Okay, this is the second hour of Physics 1C for October 4th. Okay, so we just came up with this calculation of, or this derivation of how to find the capacitance of a parallel plate capacitor. I think it's relevant to use this equation really quickly here to do a calculation so we can see how it works out. So suppose that I tell you that you have two plates with an area of 0.5 meters squared are separated by a distance of, we'll use 2 millimeters. Okay, so we have two plates with an area of 0.5 meters squared are separated by a distance of 2 millimeters. We want to find the capacitance if the region between the plates is filled with air. I say air because depending on what you put inside the plates of your capacitor, the value of the capacitance will change. The equation that we derived right here, this one works for air or vacuum. If you have air or vacuum, that's where the epsilon naught factor comes in here. There are different values of epsilon depending on the material that's in here, whether it's like paper or Teflon or, I don't know, plastic. There's all kinds of different things that you can put in between the plates here. And it will actually change the capacitance. And all you have to do is to look up the value of what epsilon is for that substance, basically. So anyway, we're going to do one for air or vacuum just to work with stuff that we know about so far. And we'll put off putting things in between or dielectrics until a little bit later. So, okay. All we need to do here is to just directly plug the information that we have in the problem. So the capacitance should be equal to epsilon naught, which is 8.85 times 10 to the negative 12. And this is Newton meter squared over Coulomb squared. No, it's the inverse of that, right? Yeah. It's Coulomb squared over Newtons times meters squared. So that's epsilon naught. We multiplied by the area, which is this. And then we divide by 2 millimeters, which will be 2 times 10 to the minus 3 meters. And this should give us a value for the capacitance, which is what do y'all get if you do this calculation? What do you get? Okay. Now what about the units? Let's look at our units here. There's a meter squared here, and there's a meter squared there. Those cancel out. There is a Coulomb squared divided by Newtons times meters. So somehow we have to prove that this has the same units of coulombs divided by volts. And it should, if we work it out. And the way we can do that is to kind of go through steps here where we replace things one at a time. Let's just look at the units. So instead of placing an equal sign right here, let's just look at the units themselves. So what do we have? We have, so coulombs squared over Newton meter would be the same thing as coulombs divided by a Newton times a meter is what? What's a Newton times a meter? Is that a familiar? That's a joule. Yep. Okay, so now we've got coulombs squared over joules. How is this going to work out? Well, you may or may not remember that 1 volt is equal to a joule divided by a coulomb. So this could also be written as coulombs over joules times coulombs. I know that this looks really confusing. I just look up here and I realize something. This has to be confusing you all. This is capacitance, right? And this is coulombs. Same thing, right? Kind of confusing. Nothing I can do about that. I didn't come up with this system of units. Anyway, what I'm doing down here is just units. Okay, so these are coulombs. And then obviously coulombs and joules and stuff, right? Okay. So coulomb squared over Newton meter is coulomb squared over joule, which we can write as coulombs over joule times coulombs, which we could write as coulombs divided by joules per coulomb. That'd be the same thing, right? Which is to say this is coulombs divided by J over C is volts. And that is a farad. So our answer in this case is that the capacitance, I'll just write this, the capacitance is equal to about 2.2. And because it's times 10 to the negative 9, the easiest way to write this is by using nanofarad. The symbol for farad is capital F. Does that make sense? This is a pretty big capacitor, and it's pretty close together, the plates are, but yet the value of the capacitance still came out really small. Now, you don't have much of an understanding of like what big capacitance or small capacitance is. My point is just like it's in the nanofarad range, right? This is why I said that 1 farad is a huge amount of capacitance. So most of your answers in problems and things you're going to be dealing with in problems are going to be microfarads, nanofarads, stuff like that. So yeah. Does this all make sense? Does anyone have any questions? Trying to hammer home the basics here so we can go on to harder things. Any questions? Capacitance is determined by how big the plates are, how close together they are. So, right here we have this FET simulation, and we're gonna do. Is this the one where I could do multiple capacitors? I don't think I can. Can I? What is this one? Just adds. Okay, well I know there's a way to do it. Is there another one of these? What if I get rid of this? Hey, yeah, there is another one. The question is it still going to run? Browser compatible version. Yeah, John Travolta's. You can go look that up if you want to. It's all on the FET website, PHET. Go click around. I highly recommend it. Is this actually going to load? Looks like it is. I think a lot of these things were written in Flash, and Flash doesn't work anymore or something. Yeah, there we can do multiple with this one too. Good, 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 good. Okay, so we'll start with this. Huh. Is this other one just really way better than this one? I mean, they're like exactly the same, aren't they? It's just this one has better graphics. We'll start with this one, and then we'll move to the other one. Okay, So we've got capacitance right here. You can see that this capacitor has a capacitance of 0.3 P. What's P stand for? PF? Peta is a capital P copy. Pico is a lowercase p. So, yeah. Good guess, though. Peta is big. Pico is small. Pico is 10 to the negative 12, as Patrick mentions. Okay. So this capacitor has a capacitance of 0.3 picofarads. But we are capable of changing things. Like, I can make the separation distance get smaller. So tell me, if I do this, will the capacitance go up or down if I push the plate so that they're closer together? It should go up, right? Let's see if that's the case. It does, right? You can visually see that the bar gets bigger the closer that these objects get. There's a minimum separation distance in this case of 2 millimeters. We can also make the plate area bigger. This plate area is measured in millimeters squared. So as this gets bigger, you can see that the size of the capacitance is also getting bigger. And this is the maximum size that we can put on these things here. Now currently, the capacitor is uncharged, indicated by the fact that both plates are white, and if you look over here at the battery, this battery has the ability to change its voltage, and in this case, the voltage on the battery is 0. If I raise the voltage of the battery to 1.5 without actually connecting the capacitor, see, this is still a capacitor here, even though it's not connected up. Now with a 1.5 volt, what I can do is I can close this switch over here. Oh, I can't close one at a time? I was going to ask you all what would happen if I just closed one of these, but that's okay. If we close both of these, our capacitor is going to charge up. You can see that it did so very, very quickly here. And now it's full of positive charges on top and negative charges on bottom. We can do stuff like we can separate these things away from each other, and you can see that not only does the capacitance change, but because the voltage is held constant, so think about this. If the capacitance goes down, what has to happen to the charges, assuming the voltage is held constant? If I reduce the capacitance by pulling this away, what happens to the charge? You can visually see it, right? But I just want to make sure you understand that if the capacitance goes down, and our equation is, again, this is the equation I like to think about here. Let's copy this one real quick. Here's your equation. This is all you need to know. Charge is equal to capacitance times voltage, right? If C goes down, but this stays the same, right? So if we reduce C, then Q has to go down, right? Charge has to go down. Just remind you what those are. And that's exactly what happens. As the farther away these get, the capacitance gets lower, and as a result, the number of charges on the plate decreases. If the area of the plate gets smaller, also the capacitance decreases and the number of charges decreases. You can see it. You can see that as I increase and decreases, it almost looks like in this case that as the plate area is changing, the charge density is staying the same, but you're just getting more plate, so there's more places for the charge to go, at least from the way that it's drawing it right here. Okay. We can also have a bar chart right here to show us exactly how much charge is stored. In this case, it's 1.15 picocoulombs. And of course, we can also just visualize it down here. What else can we do? Oh, we can use this voltmeter. Is the distance between the plates isn't fixed and you change the charge, will the distance change? Huh. So you're imagining if there was a movable kind of like arm or something like that allowed it so that they could basically push it apart, and you're asking if you change the charge. So like if you physically added more charges on there, what would happen to the distance between the two? It's a good question. So you're saying, suppose this was movable, and you added more charge. How would you add more charge? You could add more charge by changing the voltage, right? So if the voltage started off like right here, and your question is basically, what happens as I increase the voltage? Will these two be attracted to each other maybe? Will they repel each other? I don't know, but I would be willing to guess that the distance between the plates, my guess is that the size of the plates, physical size, might be too large for that effect you're describing to happen, Cayenne. But I'd have to think a lot more about that. I'd have to draw some pictures and stuff. I'm not really immediately sure. Good question, though. All right, so voltage. We can do a couple things with this. I can just show you real quickly here that if I put one side of the voltmeter here and the other side of the voltmeter here, you can see that the voltage between these 2 points it says it's negative, but that's just because I need to switch the direction of these. So I put the black one down here and I put the red one up here. It tells me that the potential difference between those 2 points is 1.5. I just wanted to show you that if I come to the plates over here and I put one right there and I put one right there, that the voltage will still be the same. And that's just to say that the voltage on the plates is the same as the voltage of the battery due to these wires. We can also throw in here the electric field so we can see what it looks like. Boom, there it is. And we can also see how that electric field changes. For example, if I lower this, the electric field gets weaker. Not too surprising. Bigger battery, bigger electric field. And then we can also see what happens to the electric field as they get closer here. And you can see that the density of the field lines goes up quite a bit the closer these objects get together. Can you tell that the density of the field lines here isn't nearly as dense as when they get really close together? Just way more density there of the field lines. That means that the electric field is getting way bigger, right? Delta V is staying the same, but because electric field is delta V over D, the smaller this distance is, the bigger that field's going to get. All right, for now, I think this is all we can really do with this. What we're going to do next is see what happens when I connect a bunch of these, and I'm going to try to get you to predict the voltage that you're going to measure. But we got to learn some other stuff before we can do that. All right, that's your equation right there. Try to memorize it. I know it's tough. For me, I just remember there used to be this channel. I don't even know if... Have you guys ever heard of the Home Shopping Network? Anyway, the symbols for that channel were QVC. And that's how I remember it, is QVC. You can go whatever way you want to memorize it if you want, but you'll be using this a lot in this class. So it's one of the formulas you're going to want to memorize. This one along with Ohm's law. You're going to use it so frequently that it's a good idea to just memorize the formula. QVC. Okay. So the next thing to discuss, if you guys have any questions, please ask. But if not, I will keep going. Oh, I guess one other thing I mentioned. I told you at the beginning that capacitors can be used to release energy. I'm sorry to hear that, Michael. That's too bad. But it's being recorded, so. I told you that these can be used to release energy, but I guess I didn't really tell you how. I believe that's the point of this piece right here, so I'm just going to go ahead and show this to you. So, same situation as before. We have a charged capacitor here, right? And we're going to charge it up to the absolute maximum that we can, which I think is like that. That's about as big as the charge is possibly going to be. So here's our charged object, right? And what we can do is we can use it to light up this light bulb, right? But you're going to notice that it doesn't work as well as hooking up a battery to a light bulb. If you hook a battery up to a light bulb, the light bulb's just going to burn constantly, right? So I want you to notice what's different when a couple things here. First of all, notice that the capacitor maintains its charge even when I disconnect it from the battery. Do you all see that? It can hold its charge. Because then what I can do is I can take the energy stored in this capacitor here, those charges, and if I touch this wire right here, and I touch this wire right here, what's going to happen to the charges on these plates? They're going to move. How are they going to move? They're going to flow through the bulb, yeah. All these positive charges are right here. They want really badly to get over here and neutralize these negative charges. And if we do that, that's what's going to happen. So I'll just show you 3, 2, 1. So the light bulb's lit. It was at its brightest at the beginning, and now it's slowly dimming and dimming and dimming as we run out of charges, as we run out of energy, basically. And eventually, all the charges from the positive side over here are going to flow all the way back around here to the negative side. And eventually, there's not any charges anymore to keep the light bulb lit. So it takes some time, but eventually all the charges will flow off of it. In reality, this would occur in like half a second at maximum. Normally, this process would be super fast. And I'll show you that when we go in the lab. This is just done for, it's slowed down incredibly. I just want to show that one more time. So we charge it up, right? And now what I want you to do is to look at this energy here. This is the amount of energy that's stored. It's 1.99 picojoules. And you'll notice that that energy storage is going to immediately start to go down. Just like that. And as it runs out of energy, the light bulb won't work. How long can a capacitor hold a charge? If the capacitor is in the state that I showed you right here, so we charge it up and we leave it right here, like this. If we leave it like this, then it'll hold its charge for a while. I will say in practice it doesn't hold it that long, but it can hold it for a while. In these theoretical simulations, right? Like, it'll hold the charge forever. But to answer your question more completely, it'll hold the charge until you create a pathway for the charge to be lost or to be dissipated through the system. You know. So as long as there's no pathway, the charges are just going to stay there. As soon as there is a pathway for those charges to flow along, then they'll flow. All right. Okay, so in order to handle... Yeah, that's right. The light will lose the energy to heat up and light up. That's right. Because there's no more source. Now, of course, if we just take the same system, but we just hook up the light bulb to the battery, the light bulb will just stay on until the battery runs out of energy, basically, right? Which will be much, much, much longer. The point is that the capacitor is able to deliver... It can charge up very quickly, and then it can discharge at whatever rate you want to. That's the point. That's the point. So, it doesn't provide a constant source of power like a wall socket, but it can provide bursts of energy. In fact, some electric cars actually use capacitors to replace batteries. I don't know if you all knew that. But, you know, if you look at an electric car, the vast majority of the weight of the electric car is the battery itself. And batteries have a limited lifetime, right? You can only use them for so long. So if instead of using a battery as an energy source, you instead use capacitors as an energy source, then you can avoid some of the chemical components of the battery and stuff like that. Anyway, so yeah, there are cars that are designed to use capacitors to store a charge, which is then released later, like that. All right, so the next thing we want to do with capacitors is talk about what happens when I put multiple capacitors into a system together. And I just realized I told you I would show you what these things look like. So commercial capacitors, if you go buy them at a store, they're going to look nothing like what I just showed you. They're going to look like this. Which one of these pictures is really good? This picture's pretty good. Okay, so I'll show you. We have like a table of capacitors, and they look exactly like this, and I'll show it to you when we get to the lab. Okay, so different types of capacitors. All right, there's these ceramic types, which kind of just look like this. The most common type that you're going to see in the laboratory are going to look more like this right here or this right here, where you have like this cylindrical tube. And what happens is if you cut one of these open, then what you're going to see on the inside is something like this. This is a pretty good picture. Is there a better picture here? This one? It's pretty good, I guess. The point is that inside of the... Oh, this picture is even better. That's a way better picture. Whoa, this is such an old... What is this? Oh, this is even better. Okay, we'll do this. Open image in new tab. So this right here, we'll just put this into the notes. All right. This is what happens when you open one of them up. So I told you that parallel plate capacitors are capacitors where you have this gap like this and you have two plates, right? What they do is, in order to make the area really big, because remember, capacitance is equal to epsilon area over D, you want to make area as big as possible, and you want to make D as small as possible. So what they do is, for the diameter, or for D, you have aluminum, so here's aluminum, and then you've got some other metal plate here, right? And what they've basically done is that they've taken like a really long capacitor. I guess I could draw a picture. So say that you take a piece of metal that's long and flat, like imagine like aluminum foil, for example. So we've got like, we'll say this is aluminum. And then you take a small dielectric and you put it here. So here's your dielectric. Dielectric is like a medium. It's like air or paper or whatever. This could be like paper. So you've got, on the top here, you've got aluminum. In between you have paper, and then on the bottom right here, you just put another piece of metal, probably the same kind of metal. So down here you have another layer of aluminum. And then what they do to make it look like this is they just roll it up, like a toilet paper roll or something like that. And then you connect one side and one side, and then you get this really, really large amount of capacitors. So instead of having this huge object that's like, you know, really big, you roll it up. And then, in fact, one of the things they do with these sometimes, which is really cool, is that some of these are made without a dielectric. There's like nothing in the middle to separate the pieces of metal. But then when they run electricity through it, the metal will corrode. It'll create, you know, oxidation, basically. And so you've got a piece of metal, another piece of metal, and then the oxidation layer that's created on the metal becomes the dielectric. Because the oxidized metal, like rust, I guess doesn't, you know, conduct electricity very well or whatever. But the point is that they make this incredibly thin dielectric between the two objects by allowing the metal to just corrode at the surface, which means that the thinness is going to be incredibly, incredibly small, basically is the idea. And you can make the distance between the plates really, 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 really short. Okay, so this is what you're going to see when you go and use capacitors. And of course, when you look at these things, they have values written on them. Like this one right here, probably can't read it too well, but it says 2200 microfarads, I think. So that's a 2200 microfarad capacitor. This one it looks like 60 microfarads, maybe 680 microfarads. I can't really completely read it, but usually written on the outside of the device, you're gonna have the information about what its capacitance is. And then from there, you know, once you have your capacitor installed, like, you're probably not going to be thinking about this idea of what a parallel capacitor is. You're mostly going to be thinking about this, because this is going to be the relationship that we're going to be using to discuss these things. Anyway, so that's what a real capacitor looks like. I'll show you examples of real capacitors that are both closed and open when we come into the lab, so you'll get a feel for what these things are. Okay. All right. So next thing we want to discuss is capacitor combinations of capacitors. Which one do we want to do first? I think parallel is probably the easiest. Okay, parallel. So now I'm going to start doing circuit diagrams, and I'll show you what the pieces of the circuit diagram mean. Okay, so first of all, when I write this is a battery, or some type of voltage source. Maybe it's the voltage from the wall. Okay, that's a battery. The long side of the battery is the positive side. The short side of the battery is the negative side. That's my symbol for a battery. When I write this, with two equal sized lines, this is a capacitor. You'll also see things like this, sometimes with the letter S written under here. This is a switch. They can be used to open and close circuits. Okay. So for now, I believe those are the only symbols you're going to need to understand what they represent. But long line, short line is a battery or voltage source. Two equal sized lines is a capacitor, and then this is a switch. So what we're going to do is we're going to set up a parallel combination of capacitors. What does parallel mean? Parallel means that I have a battery. So here's my battery with some voltage that I'll call delta V. And we're going to connect two capacitors up to this. One of them is going to be right here. Okay. And the other one is going to be right on top of it. Oh, and any other portion of a circuit is just a wire. Okay. So that is a wire, basically. It goes all the way from here and connects to my capacitor here. And another wire that goes all the way up to here connects to my capacitor here. And then eventually they connect back to the battery over here. Let's say that I have a capacitance here that I call C1, and I have a capacitance here that I call C2. Okay. The question that we want to answer right here is, let's do it like this. What is the equivalent capacitance of this setup? So that is to say, suppose that I want to simplify this circuit down to a circuit where instead of having two capacitors, I ask, well, what if I want to make my circuit, what if I want to have the exact same capacitance, but I want to simplify the circuit down to just one capacitor? Another way to ask this is like, what's the total capacitance, basically? We're going to call it CEQ because that's how it's named, basically. But you could think of it as total capacitance, whatever you want to think of it as. We don't call it total because it's not just about adding up the capacitances, although maybe it is, all the time. It's not always about that. So, all right. So this is how we do this. Okay. So this is really important to understand. Whenever I connect something in parallel, okay, when I connect something in parallel, parallel means same voltage across each capacitor or each element. So what that means is that if I was to take a multimeter and measure the potential difference between these 2 points right here, the answer I would get is that the potential difference is delta V, the same potential difference as the battery down here. Okay. Same thing if I were to come up here to C2, I would find that the potential difference across these 2 points is also the same. Can you see why that's the case? Each of these capacitors has its own independent connection to the battery, right? Basically, this point, we can draw a line and we can come straight up to this capacitor without ever touching the other capacitor. Does that make sense? So I start here and I go in a loop. I go around, 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 and I realize that I can get all the way back to the battery having only passed through one capacitor. That's basically what the definition of parallel is. Likewise, I can start from this point right here and I can draw a smooth line that goes up my circuit, goes through the C2, comes back down my circuit, and gets right back to the battery again. That's what parallel means, is that there's a separate path that I can travel along to get from the battery to my circuit element back to the battery again. It has its own personal connection to the battery, basically. It can get what it needs from the battery when it wants it without actually interfering with C2 getting what it needs from the battery if it wants it. Parallel connections are how home networks are designed. When you plug in your TV, you don't want the functioning of the TV to affect, for example, the lights in your home. And you don't want to have your microwave stop working because you just turned on your TV, for example, or something like that. You know what I mean? You don't want your blender to power down because you turned on your TV. You don't want one element of a circuit in your house to affect another element of the circuit in your house. And so as a result, everything in the house is plugged in parallel. And you'll notice that for something to be in parallel, it has to have a connection to the positive side and a connection down to the negative side here, right? And that's why when you plug something into a wall socket, there's two holes, right? One for the positive side and one for the negative side. And a third hole for ground, but we don't have to worry about that for now. The point is that most devices you just plug in, there's two little things you plug in, and you plug them in parallel to your home network. That guarantees that every piece of your home network gets the exact same voltage across all elements. The power that comes out of your wall socket has about 110 volts of RMS voltage, and anytime you plug something into the wall, it gets 110 volts. That's just how it works, because everything is plugged in parallel. Any questions about what I mean by parallel before we start doing some math? Does it make sense, what I mean by parallel?
Yeah, explaining it with the circles helps me visualize it, because I was looking at things way differently when I was doing the homework.
Okay, good. Okay, so same voltage across all the elements, and that's the important thing for this here, okay? All right. So the other thing is that when I have taken this this combination of two capacitors here, and I've reduced it down to just one capacitor, now what I can say is that for this capacitor, it's going to have some charge that I call Q, okay? And coming back over here, I'm going to say the charge on the top one is going to be Q2, and I'm going to say the charge here is going to be Q1, okay? And the relationship that I'm going to say is that if I combine these two capacitors together, one having a charge Q2 and the other having a charge Q1, that when I do so, the total charge they have when I combine them together, Q, should be the sum of Q1 plus Q2. That is to say, we can't have the charge vanish from the universe just because we combine them together. The total charge contained on this object has to be the same as the individual charge Q1 plus Q2, basically. Then we can use our equation. The equation is Q equal to C times V, right? That's the equation. So instead of Q right here, I can write the equivalent capacitance, CEQ, times delta V, which is the potential difference across its plate. Instead of Q1, I can write C1 times delta V. And instead of Q2, I can write C2 times delta V. And then I can see that all of the delta V's will cancel, and we come up with this nice, simple result. The equivalent capacitance, when you have parallel plate capacitors, is found simply by adding the individual capacitances. So for example, if C2 had been equal to, let's say, 5 microfarads, and C1 had been equal to 2 microfarads, then CEQ would be what? Seven. Yeah, it's easy. Just add them. 7 microfarads. Super simple. Now, if I were to stack more capacitors on here, every capacitor that I stack on here, you just keep adding them. Really simple. This is the easier one. Okay, any questions before I move on? We will do problems with this stuff, I promise, but we need to do both. But we did kind of just do a problem, right? All right, the next one is for a series combination. So the series combination is connected just kind of how it sounds. You're going to put one capacitor here, C1, another capacitor here, C2, and we'll obviously have a battery as well down here, delta V. So we've got our battery plus minus, And now series means I connect this one to this side, and then I connect these sides to each other, and then I connect this one back to here. All right. And now what we want to figure out is, same thing, how do I take this system, reduce it down to just one capacitor, with a capacitance that we're going to call CEQ. And the question is, what is that equal to, and how is it related to the capacitances C1 and C2? So here, I know for a fact that because these things are connected in series, the voltage across each of these has to be different. So I'll call this one delta V1, and I'm going to call this one delta V2. Okay. What I know is that whatever those voltage drops are, they have to sum up to the total voltage difference at the terminal. And one way to easily see that is if I told you that the potential difference between this point and this point was, like if I told you this was 10 volts, and I told you this was 6 volts, and I told you this over here was 0 volts, right? Then the potential difference across this one would be what, 4 volts? And the potential difference across this one would be, it's actually negative, it would be negative 4, but whatever. We're not worried about that for now. The potential difference across this one would be 6 volts, right? But 6 plus 4 is equal to, what, 10? So that would have to be what this reads. And that's easy to see because if I was to just connect a multimeter between this point and this point right here, what's the potential difference? Well, it's 10 and it's 0, which is the same as what we have on the battery here. But instead, if I connected the potential difference between here and here, I would get 10 and 6, so it's 4. And then if I did this one right here, I would get 6 and 0, which is 6. So then, 6 plus 4, you get 10. Very easy to prove with numbers. Does that make sense? I'll leave the numbers on there for a second. I'm going to erase them, though, because we don't need them. Basically, does that make sense why this would be true? Very easy to test for yourself in the lab, too, that this always works. It's just the nature of how these things are set up. Okay, let's get rid of all that stuff. Okay, so here's our setup. We have these two objects, delta V1, delta V2, C1, C2, connected in series, and this is the relationship that we have right here. So now the thing to talk about is the electric charge. How much charge is actually going to be on here? Well, suppose that I tell you that the charge on this plate becomes positive Q, because after all, it's connected to the positive side of the battery. And I say the charge on this plate becomes negative Q, okay? And I tell you that probably these charges have to be equal to each other. Why is that? Well, if there was more charge on this plate on the left side than there was on this plate on the right side, charge would actually kind of have to flow from the bigger positive side over to the negative side, because there's this nice continuous path where that can happen along, until they balance out. What about the two plates in the middle? Well, if this one's negative, it's going to attract positive charges to this side of the plate until you get the same amount of charge on this side as you do on the right side. And if this plate's positive, well, we can even just say that if this plate is negative and it pulled these charges here, it's going to leave this plate over here as being negative. So what we can take away from this is that these capacitors will have the same charge. Series combinations of capacitors, the way that they work is each element has the same charge. Voltages are different, charges are the same. These are the two things that distinguish series versus parallel, okay? Parallel, you get the same voltage across each element. For series, each element has the same charge. So parallel, same voltage, series, same charge. Be sure to memorize that, as it's not going to be something I write down on an equation sheet. It's just something you need to memorize to solve these problems, okay? So capacitors in series have the same charge. Capacitors in parallel have the same voltage. You gotta remember that. You just gotta commit it to memory. Later on, we're gonna learn that resistors that are in series carry the same current, and that resistors in parallel also have the same voltage. So these concepts aren't going to go away. We're just going to keep using them. So you'll get used to it, but just be sure you remember it, because it's just how these things work. Okay, so since I know they have the same charge, Now, when these two objects condense down into just one, this one will also carry the same charge Q. In fact, this would be the plus side, this would be the minus side. Because what's going to happen is if I push these two capacitor plates together, the negative charge and the positive charge in the middle will just annihilate. They have a total charge of 0. So just left with the outer plates right here. That being said, let's again use our equation. Our equation tells us that Q is equal to C times delta V. And we can solve this for delta V to say that delta V is going to be equal to Q over C. And then we can fill out this equation down here. Delta V1 is equal to the charge on that plate, which we called Q, divided by its capacitance, which is C1. Delta V2 is the charge on that plate, which we called Q, divided by its capacitance, which is C2. And then the total delta V that we're going to get over here is going to be the charge there, which is also Q, divided by the equivalent capacitance, CEQ. Just basically using this equation over and over again. Then we can rewrite this like this. That is the equivalent capacitance that we're going to get because all these charges are going to cancel. And in general, if I have a system where I have like 3, 4, 5 capacitors that are all connected like this, then I just keep adding up the inverses and then take the inverse. And that's our equation for the equivalent capacitance of multiple things that are connected in series. So we've got that's for series. And then we got the one that's above here, which is for parallel. So parallel is easier because you just add the capacitors. Series, you have to do this. Does that make sense? Maybe we use some example real quick here. So if C1 was equal to 6 microfarads and C2 was equal to 3 microfarads, what would CEQ be equal to? Can you all use that equation and tell me what you get? Feel free to go ahead and type the answer as soon as you get it. Is it a half? Is that what you get? I think it's 2. But if you got a half, I understand why you did. Maybe you can't see this little piece right here, but there is a raised to the -1 power right here. So not only do you have to add the inverses, but you need to raise it to the -1 power. Otherwise, the units just won't work out. So yeah, the way we do this one is CEQ is going to be equal to 1 over 6 microfarads plus 1 over 3 microfarads to the -1. I'm going to leave it in microfarads because we're looking for capacitance, right? We don't need to convert it. So a sixth plus a third, I believe, is a half, right? In case you have a historical fear of fractions. We get a common denominator here. 1 over 3 is like 2 over 6. 2 over 6 plus 1 over 6 is 3 over 6, which is 1 over 2, which we take the negative, or we raise to the -1 power, and we get an answer of 2 microfarads. You'll notice that the answer we got, 2, is less than either individual capacitance, right? So whereas when you add capacitors in parallel, you're increasing the capacitance of the system, by adding capacitors in series, you actually decrease the capacitance of the system. Isn't that interesting? You'd think by adding more stuff, you just make it bigger, right? I mean, with mass and matter, that's the way it works. If I have a box and I start loading stuff inside of it, the more mass I put in there, the heavier it's going to be, right? There's no type of mass that I can put in that's like negative mass. But in this case, by adding capacitors in series, you can alter the capacitance of your circuit. And you'll see a lot of homework problems where it's like, what type of capacitor could I add in series to reduce the capacitance of this circuit to 2.3 microfarad or something, you know? It's the kind of stuff that you're going to see. So by adding things in series, you lower the capacitance. By adding things in parallel, you increase it. All are the distinct advantages to each arrangement? The only thing I can say about that is that, what I was saying about your home circuit in your house, which is that your home circuit's connected in parallel. The advantage of connecting something in parallel means that, it allows each individual element to get its own connection to the power source. That's one advantage. The other thing I'll say is just that I think one of the main reasons why we study this is that it helps you to understand that you can manipulate the capacitance of your system if you need to by by adding additional capacitors inside of it. And also just to understand how circuits work whenever you start to put multiple components together. Because, if you were to open up your computer or a radio or an amplifier or any type of electrical device that you can find, you break it open, you look inside of it, there are very complex circuits that are happening inside of there. And a lot of the reason why we're even studying what we're doing here is because this is the way that in the past, this is how we kind of introduce you to circuits, is by starting off by showing you how capacitors work, and then we'll introduce resistors and showing you how electric current flows, and then we'll introduce something called an inductor, and we'll kind of like bring them all together so we can start building things like radios and things like this. And does that help to answer your question? I don't know if it helps to answer your question. It's less about a distinct advantage of one or the other. It's more about kind of learning about how individual electrical elements can influence each other. That's, I guess, maybe a better answer to your question, is that having a capacitor here, a capacitor here, they're going to affect each other. I guess is one way to talk about it. And what we'd like to understand is what happens when I put together a bunch of different things. Can I use that circuit to do something for me, right? Can I use that circuit to, I don't know, calculate the number of digits of pi, right? Or can I use that circuit to power my home? And we can. Yeah, we could do both in the same setup, exactly. And that's exactly what we're going to do, Josh. That's exactly what we're going to do with all of the problems that we have left over here. So what I'm going to do is probably do... Doesn't really matter. These are we'll do both of these, I guess. But yeah, so here's an example of where we have both in the same, right here, and another one here. We're going to do both of these. We'll start off with this one. So this problem says a capacitor network. What an amazing name for a problem. Find the equivalent capacitance of the 5 capacitor network shown in this figure. So we have a 12 microfarad, a 6 microfarad, an 11, a 3, all connected up like this. You'll notice this picture doesn't actually have a battery in it. This one doesn't either. So it's just the capacitors by themselves. And we need to find equivalent capacitance of this setup right here. What time do we get out of this class? It's like 4:20, right? We should probably take a break, right? Yeah, we took our last break around 2:30, so it makes sense to take this break now. Okay, let's take a break for 10 minutes. And when I come back, we are going to solve this problem, and then I'll put this one up here too in case you want to try it yourself. We'll solve this problem. If you want to try solving during the break, all you really need to do is to kind of go step by step. Like these two are in series, right? 12 and 6. So they can reduce down to a certain equivalent capacitance. And then you can combine that plus this because they're in parallel. And then they'll all combine down into one element that has a certain capacitance. And then you'll take this one plus the 9 and they'll be in series. And that's kind of how you do it. I'll let you give it a shot. See if you can do it over the break. I don't know. If you want to take a break instead, that's fine. Take a break. Either way.